Welcome. I'm on the road today due to ISTEP testing, so my video is a little bit lower quality than normal, but I tried to use a really basic setup here, a basic template. That way you can see the contrast. I tried to make the numbers and the letters really big. There is a Drive version of this presentation on Canvas, so if you can't see the equations or something like that, please check there. The other annoying thing is I have to step towards my computer to advance the slides, so apologies there. Again, bear with me. Hopefully it's still effective. So the first idea we need to talk about, the focus of today is resistance. So that's the emphasis. But what I'm trying to do in Station 1 is talk about some of the basics that maybe we've covered or maybe we've glossed over, we haven't gotten into a ton of detail on, and just trying to clean up the little things that maybe have been going on behind the scenes during the activities that you guys have been doing, you know, whether it's wiring the walls or making the circuits last time. So essentially, conservation of charge is huge. We couldn't apply any of these ideas to circuitry if charge was not conserved. When really we're talking about the conservation of energy if we're talking about conservation of charge, because charge is energy. So definitely just some vocab stuff here. So I think we're probably okay with this, but some of the conversations I heard last time, I wanted to make sure, especially that I redefined electrical current. Movement of charge through a conductor. So a conductor is something that conducts electricity. So a current moving through something is, a charge moving through something is called a current. And when we have a closed loop, we call that a circuit. I think we've used this equation, wanted to make sure it was on the screen, make sure you could get it in your notes. I equals delta Q over delta T, which is the math way to say this. We've got current equals charge over time, change in charge over change in time. So nothing real life altering there. A new equation that I don't think we've used in class is the resistivity equation. So we've got this resistivity number that is specific to, that's specific to each problem. And there's a station, like it says here, there's a station that focuses specifically on this topic. I just wanted to cover it real quickly. So resistance is directly proportional to length and inversely proportional to the cross-sectional area. So again, I think once you get to that station, it'll make much more sense, but wanted to, again, make sure that we were on the same page, we'd seen it, we could add it to our notes. This is a slide that I was concerned about being too small on the screen. I think you can see it. Again, check that Drive version if you can't. So there are a bunch of different Ohm's laws, a bunch of different ways that we can plug other equations into Ohm's laws and things like that. So here are a couple of them. The next slide is going to show you a bunch of them, and I definitely would get that next slide from the Drive version of this presentation. So we've got current equals delta V, which is change in voltage. Several of you asked what voltage was last time. If you don't know at this point, you got to get in your book. And then so current is change in voltage over resistance. And then if we need power, if we need electrical power, now we're talking about current times a change in voltage. So just some basic equations. Let me show you the next slide that I mentioned a minute ago. I'll step over here so I'm not blocking it. So this is kind of a cheat sheet that will give you the different equations that we might need in circuitry. They're all sort of different variations of Ohm's laws. So you see there are quadrants if you're looking for power, if you're looking for voltage, if you're looking for resistance, or you're looking for current, there's a quadrant for that. And then you just look for your variables. Okay, so which variables do I have? I need amps, I need my current. Well, I've got P and I got R, so I'm going to use this one. Or I've got P and I got V, so I'm going to use this one. So we won't necessarily use all of these, but I thought it was a really good kind of quick reference to give you. Might be something that's helpful as you're working through AP Classroom and things like that. Not something you get on the AP exam, so it's not something you get on the unit test, but definitely something I can see helping as you move through. But make sure if you're using this that you also consult the AP reference sheet that you actually get to use on the test, so you're not so dependent on this that you can't do the problems. I think that might be my last slide. Oh, so there are a ton of equations in this chapter. You know, we haven't done a lot with electricity, so there's a lot of foundational type stuff that's new in this chapter. If you haven't looked at 18 and 19, please do so. Remember, we've combined two units. We had the basics of electricity, that was chapter 16 and 17. Now we're applying it to circuitry and resistance. So that's 18 and 19. And to be completely honest with you, to look at our course and exam description, there's a huge emphasis on resistance. That's why we're doing resistance stations today. So please make sure you're reading the chapters. 18 is huge, 19 is equally as huge. So if you haven't read 16 to 19, we got to make sure all 4 of those chapters we're at least somewhat familiar with. Like I said, lots of equations that I can't go through in this setting that wouldn't be productive for me to go through. If you have questions, don't hesitate to ask. At this point, you're ready to move on to Station 2, which is a FET simulation on batteries and resistors.